Okay, good afternoon everybody and welcome to this afternoon's plenary session. It's an absolute pleasure to be able to welcome the next speaker, Professor Tuomas Sandholm. Tuomas is a full professor at Carnegie Mellon University, CMU, where he's been since 2001, thereabouts. He is an extremely eminent researcher in AI, but more specifically in my subfield of AI, multi-agent systems, where he's generally recognized as doing more than any other individual to bring ideas and methods from economics into artificial intelligence specifically and computer science in general. He's been the recipient of almost every award that he's eligible for, notably the Computers and Thought Award, IJCAI Computers and Thought Award in 2003, and the inaugural ACM Autonomous Agents Research Award in 2001. His research has spanned the spectrum from pure theory right through to deployed applications, and it is perhaps his use of advanced AI and optimization techniques to build real systems that marks out his work of being a particular interest. I'll draw attention to a couple of things that he's done outside the realms of publication. He was the founder of an extremely successful company, CombineNet, which traded billions of dollars in procurement auctions. More recently, he's worked on kidney exchange mechanisms, and algorithms that he and his co-authors have developed have actually helped to save lives in North America and possibly elsewhere as well. So somebody who's got an incredible academic track record, but also an incredible track record of applied research which has had genuine real-world impact, which has clearly benefited the world. Today he's going to tell us about work that he did which achieved international prominence earlier in the year, where he built programs that for the first time were able to achieve superhuman performance in certain types of poker games. Tuomas, it's a pleasure. Over to you.
Well, thank you very much, Michael. That's a very nice introduction. It's all downhill from here. So I'll talk about superhuman AI for strategic reasoning, and this is about beating top pros in heads-up no-limit Texas Holdem, which is a leading benchmark for testing these domain-independent algorithms for solving imperfect information games. And this is joint work with my PhD student, Norm Brown, and pieces of this have, previous pieces have been done with other students, and you'll see their names on the slides as we go. All right, so imperfect information games are what the real world is. These are very different than perfect information games, let's say like Go or chess, where you have complete knowledge of what the state of the world is. These are more like negotiation or security or poker. And I'll talk a lot about applications at the very end of this talk, but let me keep that motivation short for now. So in principle, techniques like AlphaGo, which is really based on Monte Carlo tree search, or techniques like minimax search with alpha-beta pruning and so on, could be used for any perfect information game. These are domain-independent techniques, but only for perfect information games. And in perfect information games, there's this really nice property that the game decomposes into subgames. So a subgame can be solved with information from that subgame only. So for example, in chess, if you want to figure out how to play the Sicilian defense, you can only look at the subtree that's rooted at that node. And it's independent on how you should play the Queen's Gambit. This is not true in imperfect information games. And this is one of the main reasons why imperfect information games are so much harder. And when I say harder, I'm saying it in a loose sense, in that clearly there are tiny imperfect information games, like let's say rock, scissors, paper, that are very easy. But conceptually they're harder, and for a given game tree size, they're much harder. Okay. So I'm going to try to convince you that this decomposition property doesn't hold in imperfect information games. And this is a small toy example, which we will call coin toss. And this is actually going to be a running example throughout the talk. The poker games are so huge that I'm not going to try to walk you through those. So we're going to use a running example of a tiny game. So here, chance, the green node, first flips a coin, heads or tails, 50-50. Then player one, the red player, observes whether it was heads or tails, and then the red player gets to choose whether he wants to sell the coin or play. And if he chooses to play, then player 2 gets a move, the blue player gets a move, and the blue player gets to try to guess whether the coin is heads or tails. If he guesses correctly, so in the heads case guesses heads, then player 1 is going to get -1, player 2 is going to get 1. So the payoffs are always shown from the perspective of player 1 throughout the talk. If player 2 guesses wrong, for example, guesses tails when the answer is heads, then player 1 gets 1. And then player 2 can also have the option to forfeit. Say, okay, I don't know, I'm just going to give up. And in that case, player 1 gets 1. All right? This is our running example. I'm sure all of you have seen game trees, such as for tic-tac-toe or checkers or chess. In imperfect information games, we have this extra structure called an information set. What an information set represents is uncertainty as to which node the player in the information set is in. So here, the blue player, when it's his turn to move, if he gets a move, doesn't know whether he's in the left blue node or the right blue node. And whether he's in the left blue node or the right blue node depends on player 1's strategy. Player 1, on the other hand, has these singleton information sets that have only one node each, so player 1 knows exactly the state of the world when it's player 1's turn to move. All right, so now, what's a solution to a game? Well, we use the game theoretic notion of Nash Equilibrium. A strategy here is a mapping from information sets to action probabilities. So a strategy for a player says for each information set of that player, what is the probability distribution over actions in that information set? And a probability distribution is important in that you might want to have mixed strategies, in other words, randomized strategies. So at different times when you get to the same situation, you might want to play it differently, just to keep the opponent guessing. And what's a Nash equilibrium then, or a solution of the game? That's a profile of strategies, one strategy per player, where no player can improve their expected utility by deviating to a different strategy, given that the other players don't deviate. So Nash equilibrium was introduced by John Nash in 1950, and it has really changed all of economics. The beliefs here, what are the beliefs? They're probabilities within each information set that says what is the probability that we're in the first node of the information set, what's the probability that we're in the second node, and so forth. They are derived from the strategies using Bayes' rule, which is standard. And an epsilon Nash equilibrium is an approximation of Nash equilibrium where no player can improve their expected payoff more than epsilon, given that the other players don't change. So as you might guess here, if we say that the sell option is worth 0 for player 1, then one Nash equilibrium is where player 1 sells with probability half, regardless of whether it's heads or tails, and plays with probability half. Player 2 guesses heads with probability half, tails with probability half, and never forfeits. That's one Nash equilibrium. Okay, now I'm going to argue that in imperfect information games, even this tiny one, a subgame cannot be solved based on information in that subgame only. And let's look at the subgame that starts with player 2's information set here, the purple subgame. And by the way, I'm using a different notion of subgame than in game theory. In game theory, a subgame is called a subgame only if it's just a singleton information set. Here we're using more like the poker AI lingo that this is called a subgame, even if there are multiple nodes in the information set to start. Now, let's say that we're in an instance of this game where selling a heads coin is worth $2 and selling a tails coin is -2. Now, obviously, player 1 would always sell the heads coin and never the tails coin. And therefore, player 2, if he gets a move, knows it's tails and would always guess tails. In contrast, if we flip those payoffs in those other triangles which can represent large parts of other pieces of the game tree. The other way around, then with heads, player 1 would never sell, and with tails he would always sell. So if player 2 gets a move, he knows it's heads and should always guess heads. So again, based on what happens in these totally different parts of the game tree, which are these triangles, which can be very far in general from this subgame, totally different things should be done in subgame. So this is one of the main reasons why imperfect information games are so much more difficult than perfect information games, and the techniques for perfect information games don't apply at all. Okay, so how do we tackle these games? Well, first of all, the techniques that we use are domain independent. These are not techniques for poker, these are techniques for general imperfect information games. So you can think about the input as being that type of representation where you have a tree with information sets or some more compact, abstract text that describes the rules like that. Techniques for complete information games don't apply, as we discussed. There are extra challenges here. There's uncertainty about what others and chance will do, but more importantly, there's uncertainty about what others and chance have already done. That leads to hidden state. So I don't know what my opponent knows and vice versa. Therefore, I am going to have to think about how do my opponent's actions signal to me about the private information of the opponent. And conversely, I'm going to have to think about how do my actions signal to my opponent about my private information. The nice thing here is that we don't have to assume what the signals mean. The meaning of the signals automatically falls out from the definition of Nash equilibrium. However, Nash equilibrium doesn't do anything. It's just a definition. It has to be married up with AI algorithms to actually compute these solutions before it's operational. And that's really what this talk is about. Now, poker has a long history in game theory, AI, operations research, and mathematics. So if you go to John Nash's Nobel Prize-winning dissertation where he introduced Nash equilibrium, it's a very short document, so I recommend reading it in detail, you'll find out that he had one application there, only one, and that's poker. So he realized early on that game theory is not about chess, it's about imperfect information. Now the game that he was looking at is Coon Poker, which is a tiny game with 3 cards in the deck. Everybody gets, both players get 1 card, so this is something you can solve by hand. But still, he recognized that this type of reasoning in imperfect information games is very important. Then there's been a whole long history over the last few decades in AI, game theory, operations research, and so forth, of working on poker. Just to highlight one piece, there's a great IJCAI17 paper by Billings et al. I think I see Jonathan Schaefer in the audience there, and so forth. Jonathan played a big role in the AI community in working on poker from the early 90s to early 2000s. And then the field really exploded in the last 13 years. There have been hundreds of papers published, and I'm not going to try to do a literature review here. Let me just mention a couple of highlights. One is that with my student Andrew Gilpin, we solved Rhode Island Holdem exactly, which was an AI challenge problem introduced by Shi and Littman in 2001. And the technique was called automated lossless abstraction. Seems like an oxymoron that you can actually abstract the game and get a lossless answer, but you can do that to an extent. Actually, you can get rid of about 99% of the game, and you'll still get an exact answer. That, of course, doesn't scale to large games like Heads Up No Limit Texas Holdem, but for Rhode Island Holdem, which had 3.1 billion nodes in the game tree, we could solve it exactly. This was 4 to 5 orders of magnitude bigger than the biggest game solved before. Then in 2006, the annual computer poker competition started, hosted always at AAAI, and this really drove the competitive research in that the different research groups could compare performance against each other, performance year to year, publish their results, and build on each other's results. And then in 2015, Bowling et al. Almost optimally solved Limit Texas Holdem, which after lossless abstraction has 10 to the 13 different information sets. So this is just on the cusp of being small enough that with a small supercomputer and clever algorithms, you can brute force through it a couple thousand times and get a near optimal answer. That was kind of a breakthrough. Now, heads-up no-limit Texas Hold'em is a whole other animal. It's the main benchmark and challenge problem in AI for imperfect information game solving and has been for the last several years. It has 10 to the 161 different situations that the player can face. So 10 to the 161 information sets. That's a big number. So it's more than the number of atoms in the universe, and even if you had for each atom in the universe a whole other universe and counted those subatoms, it's even more than that. So you're not about to write this down or brute force through it even once. This is mostly played on the internet, so you don't see this as much on TV as you see other kinds of poker, but it is very popular, and you'll see it in some movies like Casino Royale or Rounders and so forth. And top players actually think of this often as the purest form of poker, because there are no other players that are messing the game up. It's really just, Michael, are you a better poker player or am I? And it's mano a mano. No prior AI has been able to beat top humans at this game. So I'm not going to actually go through the rules in detail. I'm just going to give you one slide on this just so you know enough to follow the rest of the talk. So there are two players. First, chance deals 2 cards to each player in private. Then there's a round of betting. And whenever you bet, you can bet any amount up to all of your chips. So the branching factor is huge. Then chance deals 3 shared cards on the board face up. Then there's another round of betting. Then chance deals 1 shared card on the board, a 4th one. And then there's a round of betting. And then chance deals 1 more card, the 5th card, onto the board face up. And then there's a round of betting. And the player with the better 5-card hand made out of his 7 cards wins. Unless somebody folds, in which case the person who folded loses the hand. And then you go again. The number 10 to the 161 is really the size of 1 hand of this game, which is described on this slide. Okay, so as Michael mentioned, this January I organized this Brains versus AI rematch to play against the top humans at this game. And I'm calling it a rematch because I had done a similar thing in April and May 2015, where we took our prior AI called Cloudico, which was the best AI for this game at the time, and we tried to beat the best humans, and we couldn't. So now this was our, hopefully a revenge match. Of course, we had no idea whether we actually were better than the humans at this point, or whether we even could tell, or whether we would be so close that we wouldn't know. So our AI was called Libratus. Its Latin stands for balanced and forceful. Balanced because it's an approximation of Nash Equilibrium, and forceful for 2 reasons. One is that it plays a strong poker game, but also it plays a very powerful poker game, a very aggressive form of poker that humans don't usually play. We challenged 4 of the best heads-up no-limit Texas Hold'em specialist professionals to come and play. And this is important. There's a big difference between, the average person and the average serious poker player. Then there's a big difference from that to the average professional. Then there's a huge difference from that to the average heads-up no-limit Texas Hold'em heads-up specialist. And then there's a huge jump to the top heads-up no-limit Texas Hold'em professionals, of which there are only 10 or 20 in the world that are really in that top category. And if you see, many of the people you see on TV would get completely trashed by these people if they actually played. And they do. So the 4 players that we played against were the following. The pictures are right there. First, Dong Kim, originally from South Korea, mostly lives in Vegas nowadays. He's recognized as the #1 or 2 player in the world. Jason Les, also very well known, originally from California. This summer in the heads-up Texas Hold'em event of the World Series of Poker, he ended up in the round of 16, so you could say he was 9th. And he's won a lot of other games as well in this form of poker. Jimmy Chou, originally from China, now lives in Vegas, has won a lot of events in this kind of poker. And Daniel Macaulay from Scotland, he is one of the 2 or 3 people in the world who will play anybody. So if you want to play him on PokerStars, I'm sure he'll be happy to take you on. These people's lives are actually quite interesting, and you might think that it's glamorous, but it's maybe not, in that they are always on call to play poker. So they sleep with their laptops, they even go in the shower sometimes with the laptop ready to go in case somebody's willing to play. They're always sitting in the lobbies of these poker sites ready to play, because it's very hard for them to get action because everybody knows how good they are. Okay, so we played 120,000 hands over 20 days in January 2017. So each one of them played 30,000 hands, and it's important to play a lot of hands for 2 reasons. One is to get statistical significance. There's a lot of variance in here coming in from luck, and even with certain variance reduction techniques that we used, like duplicate matches and equity splitting, if you know what those are, you still need a lot of hands to decide who's actually better. And in the 2015 match, we played 80,000 hands, and we couldn't quite get statistical significance. The humans won, but not with statistical significance. So we increased the number of hands by 50% to 120,000. My worry was that now, if the humans were better in 2015 and we were worse, now we're better, maybe the humans are also better, but maybe the gap is smaller, so now it's even harder to figure out who's better. Going in, that was my worry. We paid the pros $200,000 in aggregate for participation. We weren't allowed to gamble. The Pennsylvania gambling board didn't really like the idea of gambling, so gaming board. So we actually paid them a participation fee, but we didn't each give them $50,000. Instead, we had their payout depend on how they did relatively to each other when they played against Libratus. So they had not only the pride of mankind on their shoulders, which they took very seriously, but also a little bit of a financial incentive to play as hard as they could. And these are very serious athletes. So this idea of a poker players wearing a Stetson hat and smoking cigars and drinking whiskey, no, not these guys. These guys were eating oatmeal, stretching, taking care of their sleep hygiene, and so forth. We also set up very conservative experiment here in that we favored humans in many different ways. And this is actually a long story we can talk about afterwards. But what we didn't want is a Deep Blue Kasparov style thing that happened in '97, where after the match the humans said that actually this wasn't fair. This was somehow rigged against the humans. And some of the things include that the humans were allowed to think as long as they want, they were allowed to take breaks if they felt tired, and many other aspects like that. If they misclicked, we canceled the misclicked hands and all of that. All right. So this is what it looked like. Here's the casino floor. We did duplicate matches, so 2 of the players are playing on the casino floor, 2 are playing in an isolation room on the 2nd floor of the casino with no communications. Here we're having some fun. This is what it looks like. Jason is here playing 2 copies of Libratus at the same time, so when Libratus stops to think, Jason can move on to the other board, so he doesn't have to wait. And the 3rd little monitor, there is the Twitch chat where his fans are cheering him on. Okay, so what happened? First of all, so I was worried that this could end up in a statistical tie again, like what we had in 2015. What did other people think? Well, the international betting sites thought that we would get completely destroyed. We were a 1-4 or 1-5 underdog the morning of the event. But here's what happened. So Libratus beat the top humans in this game by a lot. We beat them by 147 millibig blinds per hand. The statistical significance of the win was 99.98%, or p-value 0.0002, or if you like, 4 sigma. So clear statistical significance. And also each of the humans individually lost to Libratus. Okay, so this was the first time that AI had been able to beat top humans at this game, and still the only one. Then I get a call from China saying, okay, that was fun, really fun, interesting, fantastic, great, we want you to come and do this in China. And I said, well, we already beat the best, why would we do this? And said, okay, well, fine, we'll not make it a real competition, we'll do it as an exhibition. Okay, so we did an exhibition of 36,000 hands against 6 Chinese players, including China's one and only World Series of Poker bracelet winner, who was their team lead. And the players weren't just poker players, they also had expertise in computer science and machine learning. And when we got there, we thought this was going to be an easy 4.5 days. Turned out when we got there to the event site, it was a whole building. They actually had studied the hand histories, the 120,000 hands. I don't know how they got that stuff, because but they had that. They had analyzed all of that. I saw an extra room, kind of door closed there. Opened it. There's this long table with 10 analysts on computers analyzing live what's going on. So these guys were very serious. Anyway. So Len Pudashi, which was the brand that we played under, won by 220 millibig blinds per hand. So even more than in January. And this really speaks to the quality of the players we played in January, that they were actually able to play so well. Although they also used computational tools in their analysis and consultants. We won each of the 9 sessions and also beat each of the humans individually. All right, so for this audience, it's probably interesting to know how does Libratus work, or Link Pudashi, which is just a slight variation of that. So I'm going to talk about that for the rest of this lecture. All right, so Libratus has really 3 main modules. The first one takes the rules of the game as input and outputs what we call a blueprint strategy, which is like a coarse Nash equilibrium for the whole game. It has 2 parts, abstraction, automated abstraction, and then equilibrium finding. I'll talk about that. The second module takes the blueprint strategy, and by the way, the first module, think about running for months. So we were running throughout 2016, at least the second half. We spent about 15 million core hours on that module. Then the second module is subgame solving, where in real time during the play of a hand, the AI stops to think and refines its own strategy for the subgame. And think about 10 seconds to 45 seconds as a time scale of that, still on a supercomputer. And then the last module is a self-improver, where that you could call that kind of the one and only machine learning piece, where there's some amount of learning going on. But oftentimes in poker and imperfect information games in general, the goal of the machine learning is to try to exploit the opponents. So figure out what are the opponent's weaknesses and try to exploit those. I thought that would be a really bad idea here. We're playing the world's best players, so they don't, first of all, have many weaknesses, at least not very obvious ones that are easy to detect. And secondly, they're world's leading experts at counter-exploitation. So if we start to tweak our strategy to exploit them, they will actually see that and counter-exploit us. So we didn't turn on our opponent exploitation algorithms at all. Instead, what we did, we said, okay, let's take the data of how they played and infer from that data what holes they have figured out in our strategy, and then fill those into play even closer to Nash equilibrium, even closer to game theoretic optimal in those spots. And think about that as an overnight process. I'll talk about each one of these in detail. Okay, so the computing hardware, this is the newest supercomputer called Bridges at the Pittsburgh Supercomputing Center. Overall, we computed about 25 million core hours and 2.6 petabytes of data at the peak. Same supercomputer used for all of these 3 modules. So now let's talk about the first module in more detail, and then we'll talk about the rest. Okay, so the standard technique for solving, by now standard technique, for solving these large imperfect information games is to first abstract the game algorithmically to a smaller game that you can then approximately solve with an equilibrium finding algorithm for epsilon equilibrium, and then you map it back to the original game to get what we call the blueprint strategy. Sometimes that's also called the trunk strategy. All right, the particular abstraction techniques used in Libratus are the following. So there's card abstraction and action abstraction. Card abstraction just means that we are bucketing similar card histories together, and we're forcing liberators to play the same way in each bucket. That makes the game smaller and can lose some accuracy. The abstraction algorithm that we use is the same as we used for Tartanian 8, a baby version of which won the annual poker competition in 2016, and it's completely automated. But here, because we have a better equilibrium finding algorithm now than we had back then, we can get much finer grained abstraction. And in the first and the second betting rounds, there's no card abstraction. So the AI has a perfect understanding of the cards in those betting rounds. And in the third and the fourth betting round, there's some abstraction. But by the time we get there, the endgame solver is going to kick in and is going to refine the strategy without any card abstraction. So the first time ever, there's a poker AI for this game that now can actually, for every spot where it plays, have a perfect understanding of the cards. The second part is action abstraction. So in no-limit Texas Hold'em and in many applications, there is a large or even an infinite branching factor. So you can only afford to include some of the bet sizes in the abstraction. And what we do is we largely base that on what top humans and top AIs have done in the past. Also, we added some radical bet sizes just to see whether they would be a good idea. The equilibrium finder can always put 0 probability on those if it wants. And then we have a technique that provably optimizes bet sizes, but it's not very scalable. So we actually only use it for a couple of the early bet sizes to optimize the bet size. So for example, we know what is the best opening size. All right. Then our equilibrium finding algorithm to solve the abstract game is the following. It's an improvement on Monte Carlo counterfactual regret minimization. So most of you probably know what regret minimization is. Counterfactual regret minimization is taking regret minimization into sequential imperfect information games. That's a paper in NIPS 07 by Zinkiewicz et al. And it's very clever in that instead of thinking about the whole strategy space of contingency strategies that you're minimizing regret over, you can actually localize the regret minimizers on each information set. Monte Carlo means that this is sampling based, you don't have to traverse the whole full game tree. And that's by Langtot et al. Our improvement is that we start visiting less often paths during the run where our own actions don't look promising. In other words, if our own actions have very negative regret. This leads to a big speed up, and therefore we can solve larger abstractions. Also, there's a second effect which is actually maybe more important, which we didn't realize up front. So the abstractions that are used by all of the top bots nowadays are what's called imperfect recall abstractions. There, you intentionally forget some of the details of the past so that you can computationally afford to have a more detailed model of the present. But that gives you an imperfect recall game as the abstract game that you then need to solve. Here, as the algorithm starts to discount some of those paths, the in degree to these imperfect recall buckets decreases, and that problem of imperfect recall gets mitigated. The algorithm is distributed across 196 nodes. One is a head node that handles the top of the game tree, passes information to the child nodes, and they pass information back, and that's how the iteration works. The same algorithm can be applied with any number of nodes and a hierarchy of more than 2 levels as well. By the way, each compute node, its node is a term from supercomputing. You could think of it as a server with 28 cores. Okay, so that was the first piece, how we compute the blueprint strategy. The second piece, which is perhaps the most novel piece of the architecture, is the subgame solver. And now it has 5 new ideas. The first is what we call safe subgame solving, taking into account the opponent's mistakes in the hand so far. That's a mouthful. And for this piece, I'm going to actually go into a little bit of technical depth. And this is the only piece. So if you, at some point, don't follow, that's okay. We'll get back to the high level after that segment. Okay. And what I'm going to do, instead of presenting just the newest of the new, I'm going to do a transformational analogy throughout the history of endgame solving in imperfect information games, which is not very long. It's like 2.5 years old. Okay. So let's start with what we call unsafe subgame solving. So again, we're back to the coin toss example. On the left here, we have the blueprint strategy, and it's not an exact Nash equilibrium. So the equilibrium finder has given something approximate. You can see that there's mistakes in there. The second player is forfeiting with some probability. The first player is maybe also not playing optimally. And here we're looking at an instance of the game where selling the heads coin is worth half, selling the tails coin is worth -half. Now, what we do to figure out the strategy for player 2, which is Liberatus in this case, we construct what we call a gadget game, where we say that chance plays according to that trunk strategy, and then based on base rule, we can figure out what's the probability of being in the left node versus right node, and then we're going to just optimize. We're going to solve this gadget game. So no surprise there. Given that the first player is going to play more often with heads than tails, we are going to see that we're more often in the left node than the right node, and our best strategy is to always guess heads. Of course, that is wildly unsafe, because if the other guy figures that out, he can win every time. Nevertheless, unsafe subgame solving does fairly well in practice in some games, including some poker games. So this is the version of subgame solving we had with Claudico in 2015 when we went against the humans, and we didn't really know whether it worked well. In some papers we had shown that against other AIs it actually helped a little bit, but against the top humans we actually did some experiments where in some sessions we turned it on, other sessions we turned it off, and we couldn't tell whether it was actually helping or hurting. So that was a situation in 2015. Now, the next idea by Birch et al. Is what we call resolve refinement. Again, the blueprint strategy on the left is the same, but now player 1 can choose between entering the subgame or taking the expected value according to the blueprint of the subgame. So the expected value according to the blueprint on the left is 0, and on the right it's half. So we make this gadget game where player 1 can now choose between representations, if you will. Can choose to just play according to the blueprint representation or the detailed representation of the end game, which is in a finer grain abstraction potentially. Here, just the same abstraction for simplicity. All right, and then this makes sure that the opponent's expected value for entering the subgame is no higher than in the blueprint, and this proves that the strategy is safe. In other words, strategy is no worse than that of the blueprint strategy. No more exploitable than the blueprint strategy. However, this may miss opportunities for improvement. For example, with this technique, the player 2 might still forfeit with positive probability. So that kind of smells wrong. Maybe there's something better. And there is. This is an idea called max margin refinement by Moravchik et al. From IJCAI last year. It's similar to resolve refinement, but punishes player 1 as much as possible for choosing entering rather than the alternative. So we define a margin for each private type of the opponent. In poker, it's all private hands that the opponent might have. Here, it's either heads or tails. Player 1 knows whether he's heads or tails. And the margin is the expected value of the alternative minus the expected value of entering. Okay, so again, we construct the gadget game the same way as before, but now, instead of simply attempting to make all margins non-negative, we are going to maximize the minimum margin. And now, well, here's a solution, and you can see that there starts to be some smarts in this solution now. No forfeiting, and because player 1 plays more often with tails. Wait. Okay, let me not go through that reasoning. That's kind of a long story. But you can see that there's some smarts now. However, there's still a problem. While we focus on reducing player 1's expected value for heads in the subgame to -half, so we get both of the margins to be the same on the left and the right in the gadget game, player 1 can just sell for half in heads. So we're somehow wasting our flexibility in that case. And that leads to the newest of the new, which is our reach max margin refinement, where we said, okay, if player 1 chooses play following heads, player 1 is making a mistake. Player 1 is giving us a gift of half. So in the gadget game, we can actually increase the alternative payoff following heads by half, because choosing play would still be a mistake for player 1 there. And therefore, the gadget game solver then focuses on reducing player 1's expected value for other types she may have. And that's it. So we're now taking the gifts given to by our opponent to us into account. So we are focusing on the more important hands in the endgame solver automatically. And this is not just a one-shot gift. There can be a whole sequence of gifts. Like when they made that move, they gave us a $52 gift. Then they made that move, which was perfect, no gift there. Then they made this and gave us $10 and so forth. Okay, there are two flies in the ointment here. One is that if multiple subgames are refined, which we of course do, it's not just one subgame we play over time, off-path expected values might not remain the same. And the solution here is to split the gifts among subgames by the chance probabilities that the subgames are reached. So for example here, we said that the gift was half. So now we can take it all on the left subgame to make it 1, 0 on the other, or we can take it on the right side, or we can, but we cannot take it on both sides because that would make it 1. Or we can do half on both sides. The other fly in the ointment is that the gifts might not be as large as we thought because the subgames they come from will be improved. So now look at the triangle there, because we improve our solution in the triangle later, turns out that, okay, maybe the opponent's payoff wasn't half, it's only a quarter. So now in this side we cannot take the whole half as the gift, we can only take a quarter. And the solution is to substitute the lower bound on the gift, and in practice this can be an estimate. Now, how well does this do? Well, we cannot solve for a best response in the full game. So we actually tested smaller games, and the blueprint strategy did fairly poorly. The unsafe can do great or really, really poorly. Order of magnitude better, order of magnitude worse. Result refinement is safe, max margin safe and better, and reach max margin safe and the best so far. Nested subgame solving is the next topic that we use here. Let's say that we have a game that has a big branching factor. Typically you do action abstraction. You select some of the actions to be in the model, and then you do what's called action translation or reverse mapping to map your opponent's actions that were not in your model to one of the actions in the model. And there's a whole literature how to do that. Here, instead, we do nested subgame solving, where we solve the subgame in real time for the off-tree action that the opponent took. And we construct this gadget game where the player 1 can either take the alternative, which is the best of their payoffs from the model, or entering a subgame. And this can be repeated every time an off-tree action is taken. And we actually do this. So there's not just one spot where we solve the subgame, as was done in poker previously, but we actually solve the remaining subgame in more detail every time the opponent has made a move. And there's a theorem that says that if the blueprint was a Nash equilibrium and the expected value of entering is no greater than that of the alternative, then the game with the added action is still a Nash equilibrium. So it all ties together. Here, comparison again on a medium scale game, because we can't compute best response on a full game. Best prior technique for reverse mapping, got about 1400 exploitability. Nested resolve was an order of magnitude better. Nested unsafe refinement, a little bit better. Nested max margin even better, and the best is the nested version of our reach max margin refinement. All right, also the subgame solving starts much earlier. Typically it starts on the 4th round in previous AIs. Here it starts no later than the 3rd betting round, and if the pot is big enough, it starts even earlier. There's no card abstraction in the subgame, and we can actually change the action abstraction between hands because we are dynamically solving the subgame. The value of the game is not very sensitive to the action abstraction, but the strategy is very sensitive. So when we change the action abstraction every time, we keep the human guessing as to what the strategy should be. So now let's talk about, let's play a video about Libratus's balance and the use of blockers, which are a function of the endgame solving. And here, Doug Polk is interviewing Danielle Macaulay.
In contrast to the first challenge, there was a lot of hands the first time around where the bot really just punted one off. I've seen way less of that. So what are your thoughts? How good is the bot?
It's pretty good. I mean, well, I'm losing, so if I consider myself pretty good, then it must be pretty good. But there's not really any punting. Like, I think it uses blockers well in the bluff spots. Like, I've not really picked up on anything that's too obvious one way or the other. So like, I'm genuinely impressed. Yeah, it's pretty good.
Okay. Then the last piece is the self-improver. And this is a press favorite. And this is the only place where data comes in. So this is the only place where machine learning happens. Everything we said so far is like boxing against Michael Tyson after having shadow boxed against yourself. But now we're actually taking some data. So how that works, let's say that we have this small game example here. Let's say that the opponent plays some actions that are not in our action abstraction. Then we're going to prioritize those problems based on how far they're from the action prototypes and how often they're played. Let's say that's the worst. Then we're going to solve with a coarser card abstraction and also with a backup action, so we don't assume that they always make an action. We're going to fix this part of the strategy from the trunk or blueprint. Then we're going to resolve this part, and that's going to give us a strategy for that new action. So we can actually add pieces of the game tree on the fly. And you might say, why didn't you do that up front? Well, that's just too much. But now the opponents are telling us which pieces we should actually fill in. And we do this to fill in the top K holes. How big should K be? Depends on how much computing you had. We had enough for 3 holes a night. And now this is what they say about Libratus fixing its own weaknesses. This is Jason Less.
The energy level was super high the first few days. We start off in the hole, kind of expected as we're figuring out what's going on. And then we climbed all the way back to basically nearly even. And we are like, we're in this. We have a chance. And we had like key strategy ideas, key things we were pushing against the AI. And then I guess the wheels kind of just came off the wagon. And it wasn't that our play fell apart, in my opinion. I think we've really seen a clear improvement in the AI strategy day to day to day.
Okay, and let's see what Jimmy says about.
The bot plays incredible. The first 2 or 3 nights, I severely underestimated its ability. I really thought that we were just going to find a couple simple leaks and just hammer away at it, and it would just be a easy 20 days. But it's been the complete opposite. Every time we find something, it seems.
Oops. That's not so good. Whoa. Okay. Yeah, both work great. PowerPoint doesn't. Okay, let me just. Okay, so here's some other bots. Ours on the left, others on the right. There's many more bots. These are some of the best. And Libratus was really a big jump over the prior best. Strengths, well, small bets, huge bets, and huge all-ins. Perfect balance. Of course, it's not really perfect, but it's an approximation on Nash. Weird moves like donk betting and limping, which are considered bad in the poker literature. And one might ask, is this safe equilibrium play somehow boring? Are we making poker boring? And let's ask Dong that. And this is now, it's a little bit of swearing in this video, so I apologize.
One question that's been brought up a lot that a lot of people have asked me to ask you guys is, does the bot bluff?
The bot's kind of a nit.
Bot's a nit?
The bot fucking bluffs. Or am I supposed to say that? Bot bluffs.
You can curse on YouTube.
Oh, okay, I didn't know that. Bot fucking bluffs, for sure. Gangster as fuck.
Confirmed the bot does bluff.
Can you give me an example of maybe a crazy bot bluff that we wouldn't have seen from a person?
Today he flatted a 4-bet with 5-3 of clubs. The flop came King, Queen, Jack with 2 hearts. Check, check. I turn a flush, check, check, got to set the trap. 5 river, he bets, I raise small, he 3-bet jams.
That's a pretty gangster hand.
He's real gangster, like he's not messing around. And it's like manly bluffs, like big bets, like it's pretty gangster.
Yeah, you see, I think for humans in a lot of those situations, when it gets into weird lines, like, you know, a 4-bet pot, check, 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 and then all of a sudden there's, you know, bet raise 3-bet. I think a lot of players, they kind of are a little too afraid to maybe bluff. I think we can pretty safely say that is not the case here.
Yeah, it's like maybe a little bit afraid, and also just like everyone's range is so weird that it's really hard to choose which hands, whereas it can just like go this percentage of this hand or this percentage of that hand. So like in every situation you always question like what can it bluff with, and then you like realize it doesn't really matter, like it always has bluffs.
Okay, so in the interest of time, let me skip the current and future research stuff here. A lot of different applications that we're pursuing now. Negotiation, strategic pricing, product portfolio optimization, certain areas of finance. Wouldn't it be nice if there were actually some strategy in business strategy? Next generation cybersecurity, zero-day vulnerabilities. Governments are playing these games all the time to detect those vulnerabilities and to play them out, but there's no strategy there. Wouldn't it be nice if those would actually be played strategically? Obviously, a lot of military applications and auctions, steering evolution and biological adaptation in a new project and so forth. And let me end there. Thank you.
We're pretty much out of time, but if there's maybe one question, one really, really good question. Somebody very confident over there that they have a...
All your experiments today are heads up, right?
All of the ones that I talked about today. So we have papers on multiplayer as well. But the multiplayer game is different in that it's conceptually not clear that you would even want to play Nash Equilibrium, even if you could compute it. And computing a Nash equilibrium is p-pad complete. Here it's polynomial time. Obviously it's so hard, the game is so big that polynomial time doesn't really give you anything, and even linear time would be too much. We can't even walk through the game tree once.
Okay, we should call it a day. Let's thank Tuomas again.
Thank you.